Okay, so last time we were talking about symmetry elements, point groups, and the whole point of this was to understand the symmetry of the wave function. So it's when we're talking about the symmetry of the molecule, we're looking at the atoms and the locations of the atoms, and we're using the various rotational elements and reflection elements and so on, those symmetry elements, to decide on the point group. Brianna, I have to move this monitor so I can see your faces. Okay, very good. All right, so another part of that is so we can understand the symmetry of the wave functions. So everything that the molecule does is governed by the wave functions. So its electronic structure, the electron cloud, is governed by wave functions, and they're just like you have symmetric and asymmetric wave functions in the particle in a box. You have parts of the electron cloud, say the 2p orbital is going to be an odd orbital because it has a positive end and a negative end. But then the 2s orbital is going to be an even wave function because it's positive all the way around or negative all the way around. So the different wave functions for all the different electrons in a molecule are going to have different symmetries. Vibrational motion is also governed by a wave function. There's a vibrational wave function. So when you have a symmetric stretch or an asymmetric stretch, you have these little arrows on the atoms that tell you which way they're going in the vibration. And you can look at those arrows and determine the symmetry of the wave function. Now, symmetry is not the end goal for this. The selection rules are. So remember, our whole purpose of looking at the particle in a box was to determine the spectroscopy of it. You know, how can we know something about this quantum system that we can't see using spectroscopy? And so the spectroscopy is the tool, and the way to understand it is the selection rules. So that's our end goal. We're building this whole infrastructure of symmetry so that we can understand the symmetries of the wave functions, and the wave functions govern those energy levels. And spectroscopy is the difference between the energy levels. So if we can understand something about the symmetry of those energy levels, then we know more about the molecule. And so we use spectroscopy as a tool to determine how these particles interact with light, and the way they interact with light, we can have some insight using symmetry. So that's what we're doing today, is we're looking at the wave functions and assigning Mulliken symmetry notations to them. And we're going to have a couple of examples. We'll do water and ammonia. So once again, its character tables allow us to look at the symmetries of these molecular motions. So that's what we're going to be doing today. So here's the character table. This is a repeat slide from earlier. We have the characters, that's those ones and minus ones inside the table. This upper left-hand corner designation, that's the Schoenflies notation for this particular point group. So we would do the Lewis dot structure, the Vesper shape, and then go through the flow chart and decide on the point group. And so this particular molecule has a C2V point group. Then we go find a character table that has C2V in it in the corner. And this is all of the symmetry of that molecule. It has 4 different irreducible representations, A1, A2, B1, and B2. And notice that tells you how the Cartesian coordinate system, what the symmetries are of the x-axis, the y-axis, the z-axis, and then all of the Raman motions, the scattering, where the photons come in on and leave on the same axis or come in on different axes. And it also tells us about the results of our integration. And so let's look at water, and we're looking at translation, vibration, and rotation on this slide. Now think about water. It has 3 atoms, and each one of those atoms, if you were to just look at that atom, I mean, it's independent of the other atoms. It can go in the x direction, the y direction, and the z direction. So you have 3 numbers that you have to supply for each atom. And you could pick those numbers. You could change those numbers independently. So I could change the x coordinate for the oxygen atom and not have to change the x coordinate for the hydrogens, right? So x for oxygen is independent. Do you see that? And y is independent for the oxygen, and z is independent for the oxygen. So every atom has 3 independent variables, and we call those degrees of freedom. Okay. So that's a very important term, degrees of freedom. And it's essentially saying how much information do I need to specify and what information can I change independently of all the other pieces of information. So I can change the X, Y, and Z on all 3 atoms. That means if I have N atoms, then I have 3N degrees of freedom, because every atom has X, Y, and Z coordinates. Okay. So that's our total degrees of freedom, 3N total degrees of freedom. And that just means that I have to have 3 coordinates for each atom. I can change any one of those coordinates independently. And then if they all change in the X direction, so if I increase the X coordinate for all 3 atoms by 5 angstroms, what have I done? I've moved the whole molecule 5 angstroms in the X direction. That's called translation. So the relative positions haven't changed, just everything's moved in the X direction. And if I do that with Z or Y, it'll translate in those. So that since there's only 3 axes, I'm only going to have 3 translations. You might say, well, what if one doesn't go in X? What if one goes in Y while the others go in X? Well, that might be a rotation, or that might be a vibration. So there's only 3 axes, and that means there's only 3 translations. So a translation is not a vibration. A translation is its own thing. It's the molecule moving through space. So like in this room, if we define that as X, then the molecule can move in the X direction. Now, if I give the molecule a little kick, like if I take those hydrogen atoms and I kick one in the positive X direction and one in the negative X direction, then it will spin. Okay, and so that would define rotations. And because there's 3 axes I can rotate around, there's 3 rotations. The only change or caveat to that is if the molecule is linear. And so if you have a linear molecule, think about moment of inertia. If I'm pushing on a mass, then there's some inertia there. But there's nothing off of the axis. And so there's no defined moment of inertia off the axis. And so that rotation, because there's no moment of inertia, is undefined. So there's a missing rotational degree of freedom for a linear molecule because there's no mass off of that axis. So you have rotation around X and rotation around Y, but you don't have rotation around Z because there's no mass off of Z. Okay. So we say 3 rotations, but there's a little asterisk there. If it's linear, there's only 2 rotations. Now, everything that's not a translation and not a rotation, by definition, is a vibration. Okay, so that's what we end up with down here is 3n minus 6 vibrations for a nonlinear molecule. Okay, and that 6 is the 3 rotations and the 3 translations. So we have total degrees of freedom 3n, and then we take out the translations, we take out the rotations, and whatever's left over is the vibrations. And here we have all of the arrows describing the motion in this molecule. So up here at the top, you see these arrows are along the x-axis. You see the angle of the x-axis? It's the same angle for those arrows. So those arrows are going in the x direction for all 3 atoms. And since they're all moving in X, that's translation in X. It's a little more easy to see for Y. Since Y is going to the right, then that's Y. Y, goodness, that's not Y. And then Y. So I have 3 translations. All 3 atoms are moving in the Y direction, so that's Y translation. And then here, Z. I've got the Z axis here, and all of these are moving in Z. Now, the nice thing is I can look at the character table and I can look up the symmetry of X and see that it's B1. And I can look up the symmetry of Y and see that that's B2. So these 2 are connected. If I have Y translation, I have Y symmetry, then I can look on the character table and label that motion as having B2 symmetry. Well, what does that mean? Well, if I take the motion in positive Y and I reflect it in the XZ plane, all the arrows are going the other direction. And so B2 symmetry ought to have a -1 under that reflection in the ZX plane, and it does. So we'll get into that a little bit more later. Rotation around X. So here's the X axis in this coordinate system, and this little axis is supposed to be through the center mass of the molecule. And so we're rotating around the x-axis. I draw the coordinate system off to the side, but it's really located right here on the center of mass. So y is actually right here, and z is actually right here. And this is x. So it is actually rotating around the x-axis, but it gets too busy to draw your coordinate system on the center of mass, and so we just push it off to the side to give you the directions. North, south, it's kind of like a compass on a map, okay? But its actual origin, 0, 0, 0, is on the center of mass. And then here again, going through that center of mass, we have rotation around the y-axis. And so that's designated ry. The rx is the designation for rotation around x. And then rz is the designation for rotation around z. And so you can see that those axes go through the center of mass, and we're rotating around those three axes. You can look on the character table for a C2V molecule like water, and you can see that RZ has the symmetry of A2, RY has the symmetry of B1, and RX, you can look it up and see that it's B2. So those designations came from the character table. They're pretty straightforward, right? Because you just find X. If it's translation in X, you know it has X symmetry. You look it up, it's B1. RX is on the character table too. So let me just back up and you can see, yeah, RX is here. You just come across and see B2. RZ is here, so you come across and see that it's A2. So it's real simple for the rotations and the translations. The trick for vibrations is trying to figure out the arrows that are put on the bonds and the angles of the molecule, and to determine what symmetry Cartesian system it's mimicking. Okay, so down here at the bottom, down here at the bottom, we have these vibrational arrows. Now, the center of mass can't move, because if the center of mass moves, then that's translation. So by definition, for vibration, the center of mass is still, and the atoms are moving against each other. Bonds are stretching, angles are bending, but the center of mass is stationary. So if I want to stretch these hydrogen bonds, notice these arrows are stretching the bonds. So pretend the bonds are springs, and we're pulling on both springs. And since we're pulling on both springs, that's a symmetric stretch, because both bonds are increasing. Now, the molecule would translate down if I was just to pull on those springs, and so we have to move the oxygen up just a little because it's so much heavier. So that opposes the downward motion of the hydrogens. And so we're stretching those springs in this particular stretch. That's the symmetric stretch. Let's look over here. This is an asymmetric stretch. So this bond is compressing, it's getting smaller, and this bond is stretching. So I can just draw R1 and R2. R1 is getting bigger, R2 is getting smaller. And notice how both of the hydrogens are kind of moving to the left. And so, to the left, okay? And so if they're moving to the left, then the oxygen needs to move a bit to the right to keep the molecule from translating. And so that's where the little arrow on the oxygen is why that's there. And then down here in the middle, these arrows are 90 degrees to the bond. So these hydrogens are moving and keeping the same distance from the oxygen. So that's an angle bend. So it's really just this bond angle, theta, that's changing. So if I decrease theta, those hydrogens are moving closer together, and if I increase theta, then they're getting farther apart. And so we have, these are called internal coordinates. We have bond lengths and angles, and we can change those bond lengths and angles without translating the molecule, and those are vibrations. So why are these symmetries A1, and B2? Let's figure that out. So this is a vibrational motion. Everybody write this down. When I see the arrows, we're talking about vibrations. Okay. Because later we'll do molecular orbitals, and we'll see like orange and or red and green clouds. We'll look at the electron cloud. That's the electronic wave function. So for arrows, those are vibrational wave functions. So these top ones are easy. X, Y, Z translation. You look it up in the character table. RX, RY, RZ rotation. Look it up in the character table. The ones below are easy after today. So let's look at this. I call this like component vector cancellation. So we're going to look at this symmetric stretch. We have the character table up there. We have, I've already kind of given you the answer. You see Z and A1, but we're going to see why Z and A1 apply to this stretch. So let's look at the coordinate system and look at the arrows. So the Z-axis, okay, would be, so we want to take any diagonal arrows and break it into their components, whether it's an X component, a Z component, a Y component. And so these are the Z components of these arrows. Now the oxygen is going in the Z direction, so that's 100% Z. But look at the hydrogens, they're diagonal. And so they go down in Z, so we have some down parts. The down arrows are the Z components, and then the Y components are the horizontal components, and they're both going out in Y. And what we're looking for are arrows that don't cancel out. So notice they're going in opposite directions in Y. So those Y directions or Y components cancel out. And the Z components don't. Now, what we're looking for is a change in dipole moment. So think about what do we mean by dipole? Dipole is two, right? Two poles, and we're talking about electric effect. So positive and negative poles. So we have a polar bond here. We have an oxygen and a hydrogen. The hydrogen's positive, the oxygen's slightly negative. And so if we stretch that hydrogen away from the oxygen, the dipole moment increases. Okay, and we're looking to see if there's a net dipole moment that changes. And sure enough, the hydrogens are getting further from the oxygens. And so we have a dipole moment going up and down in this molecule. It's getting bigger and smaller as this hydrogen stretches. So the hydrogens are moving diagonally away from the oxygen, but they're also getting further away in Z. And so along the Z-axis is a dipole moment that's getting bigger as the hydrogens stretch and smaller as the hydrogens get closer to the oxygen, because they do compress too. They vibrate. And so as they get closer to the oxygen, that dipole shrinks. This molecule is not charged. And remember I said for particles to interact with light, they need to be charged, there need to be an unequal population, and there needs to be a non-zero transition dipole moment. Well, charged, they could also have just a change in dipole moment, and that would satisfy this interaction with light. So a change in their charge, a change in partial positive, partial negative would account as charged, interacting with light. So as light comes in with an oscillating electric field, and it matches the frequency of vibration, this dipole moment can oscillate with light and can absorb that light. So that's what's happening. If we don't have a change in dipole moment, then light's going to go right through the molecule. It's not going to have any handle to get a hold of. So then we look at this dipole moment and we compare it to the Cartesian system, and we see that it's along the Z-axis. That's where the light should come on. When you finally figure out what little vectors cancel and the remaining thing is along the Z-axis, you know it's Z. And so because you know it's Z, you're going to go up here and say, okay, I'm going to label this motion as having the symmetry of the Z-axis. And then I can come right up here and find Z in the character table, and then I can label it A1. So that's it. If you can figure out the arrows and how they kind of cancel out or not, you can find the change in the dipole moment, and then you can find the Cartesian system that goes with that change, then you can label the symmetry. It's about 4 or 5 steps, but with practice, we're going to do all 3 with water today. Hopefully you'll be able to do this. Okay, let's do another one. Let's look at the symmetric bend. So finding those components, we have the Z-axis, and then we label those Z components for all of the arrows. The oxygen is moving along Z. The hydrogens are going diagonal, so this is going to be very similar to the one before. And if you can look at it and jump ahead, you're like, look, the horizontal motion's canceling for these hydrogens, and the Z motion's not, I know it's Z. Then you got it, okay? But if you want to draw the arrows, that's fine too. So the hydrogens are moving down, and then they're also along the y-axis moving in towards each other. But because those arrows, if you put them head to tail, right, you're going there and you're coming back, right? So those vectors add, but they cancel each other out. You're back to where you began when you add those two vectors together. So you get a cancellation of the y components, a non-cancellation of the z components, and you have a change in dipole moment. Even though you're just bending the molecule, you're sort of consolidating that charge as those hydrogens get closer together. And so it has the Z symmetry, and it's A1. Can you tell how important the character table is now? If we had the wrong point group, we'd have the wrong character table, and we'd have the wrong answers. Okay. So that means you got to know how to draw your molecules and how to assign the point group. All right, let's look at the asymmetric stretch. So we put an A in front of symmetric to mean not symmetric. Okay. Looking at the Z components, you see one hydrogen's going down, the other one's going up. And so we would draw the Z arrows on there. And then we do the Y components. Oxygen's moving in Y. The hydrogens are also moving in negative Y. And then we look at the ones that cancel out. If an arrow's going up and an arrow's going down by the same magnitude, then it's going to cancel out. Another thing too, it's typically you're canceling the vectors that are on same atoms, like we're canceling the hydrogens with the hydrogens. We're not going to cancel the oxygen vector with these hydrogen vectors. So we're looking at the vectors that are on the hydrogens, and those are the ones that are going to cancel out. So the Z's, one's going up, one's going down, so those cancel out. The Y's do not cancel. And so we do have an oscillating dipole moment that's going left and right in this molecule. As the hydrogens on this side get closer to the oxygen, then that's sort of canceling the positive charge of that hydrogen. It's getting closer to that negative, but the other hydrogen's getting further away. And so we have a dipole moment facing from one direction, and then as we reverse that vibration, the dipole moment completely switches direction. So this is a huge change in dipole moment. It's actually going through zero to the other direction as these hydrogens vibrate. So we know that the dipole moment is along the y-axis. So we go find y in the character table, and we come back and label this B2. So that's how we take the arrows and turn them into the net change in dipole moment, and then we use the character table to find the symmetry. Okay. Can I clarify anything? Something that you want to ask? Okay. So let's pause. I'm going to get photos of the group so I can learn names. So what I would like you to do is write your name on there in order. So put row, let's see, I'm going to start from row 7. Row 8, row 8. Row 7, row 6. Okay. Row 5. You just write your name at the top and pass it back. So I can tell you. No, row 4. And again, this is not for Facebook or anything. This is from me. I'm going to take your pictures, and then that way I can put names and faces together and try to learn your names. I'm bad with names as it is, and so this is my attempt to get better.
Thank you.
Okay, everybody just start grading. Alright, with the masks, yeah. Okay, row 2. 1, 2, 3. Alright, row 4. 1, 2, 3. Alright, go. I'm gonna get over here. Okay. Row 5. Hit pick up. Gotcha. Okay. And then I'll do this. Okay, row 6. 1, 2, 3. Okay, at least I'll have everybody's eyes. Row 6 here. 1, 2, 3. Okay, good. Row 7. Don't hide. Okay. Gotcha. And then row 8. I see you. All right, we're good. Thank you for indulging me. And I'll take your sheets. I'm trying to wait until the semester. All right, thanks. Okay, so now let's see what we can do with these symmetries that we have. Okay, so let's look at the vibrational energy level diagram. Remember, levels and lines are different things. This is the energy level diagram. The spectroscopic lines are the transitions, so the differences in these energy levels. So vibrational motion is similar to the particle in a box, but it's different in a very important way. Okay, so here's the energy equation. It's the vibrational frequency times the vibrational quantum number plus 1. In my earlier notes, this was N. All my quantum numbers were N. But now as we're getting into sort of real spectroscopy, every little quantum number is different. Like vibrational quantum numbers are V. Rotational quantum numbers are J. Okay. There is no quantum number for molecular orbitals. Okay. We just label them with their symmetry. Okay. There are atomic orbital quantum numbers, and you know those as N, L, M sub L, and M sub S. So we have those various designations for the electrons. Okay. But so this is the quantum number here. Quantum number. Okay. And it's a V, but the font here makes it look like a Greek character nu. So it should be a V. I mean, but it, you know, that's just the font. So the nu out front, this is vibrational frequency. This is the Greek character nu. And that tilde on top, that little squig thing, that like Enya, but it's a tilde. That thing on top is means wave numbers. I guess that makes sense. Tilde equals wave numbers. Okay. All right, so that's our energy equation. And the difference over here, you can see the difference between all of these energy levels is the same, and it's the vibrational frequency. So as the molecule's vibrating in time, then that's the vibrational frequency. It's what we call an equal ladder of states. It looks like a ladder, right? All of the rungs are the same spacing. Whereas our particle in a box went up as n squared, so the spacing was dramatically different as you went up. Okay. So the symmetries of the vibrational wave functions alternate, just like they did in the particle in a box. The even-numbered quantum states are top row symmetry. Notice if I want to speak in general terms about all molecules, I can't use A1 and I can't use AG, because only molecules with an inversion center have G's, and not every, well, I think if it doesn't have a G, I think every one of them's A1, but there are some that have A prime. So I just have to say top row symmetry or even symmetry. So in water, that's A1. So you see over there, the even numbered quantum numbers are A1, which is the top row for water. Okay. I'll go ahead and put that here, top. Okay, so that's why those are A1. If we were in benzene and it was a symmetric stretch in benzene, it'd be AG. Okay. The odd number quantum states match the symmetry of the motion. So for water, for the symmetric stretch, that's A1 too. So every level is A1. But for the asymmetric stretch, it was, what was it, B2? Look in your notes real quick and help me out. The asymmetric stretch, B2. Okay, so then for the asymmetric stretch, the odd number quantum states are B2 symmetry. So it really matters which motion we're talking about. And so it's right there, the symmetric stretch B2 in water. So those 1, 3, 5, 7, and so on are going to be labeled B2. Now this is allowing us now to set up the transition dipole moment integral. And that's one of the questions on the homework, is to do the symmetry setup for a particular vibrational motion. You asked me that on the email, yeah. And so let's go ahead and do that before. I mean, Well, it's in the notes, so we'll just wait. Let's look now. So this is the vibrational setup where the wave function symmetry alternates in the energy level diagram. Now, since this is the first time you learn how to label the energy level diagram, every year a lot of people think that this is the way it is for all energy level diagrams. It's not. It's just for vibration and rotation they do this. For the molecular orbitals, right here, the molecular orbital wave functions do not alternate in a regular pattern. Okay, so just make sure you make note of that, because we learn for vibration, but that's for vibration. We haven't learned about MOs. The MOs are different. Okay, so since MOs are different, let's look at some molecular orbitals. So here we have the ammonia molecule in the C3V character table. It's quite a different character table. We only have 3 rows. We have A1, A2, there's no B's, and we have an E. We have this strange E motion. Remember I said this was a threefold or symmetric top, which meant X and Y had the same moments of inertia. They had the same symmetry. So notice X and Y are coupled together. We call this their basis set has a symmetry of E. Same thing about rotation in X and rotation in Y. So this is going to change how we label things. Let's look at the molecular orbitals on this molecule. Now, there is a video that I have associated with this course on YouTube called the projection operator. And it shows you how we get these pretty pictures, okay? It's pretty complicated. It takes a whole lecture, it's fine. And you can go check it out if you're wondering where these pictures came from. At this point in the course, I just want you to take the pictures and look at them and see if you can figure out the symmetry of those pictures, okay? So these are the molecular orbitals. Notice here's the center of mass in the middle of the molecule, just below that nitrogen. So the symmetric axis is going to be the z-axis. So now z is coming out in front of us. In this week's lab, you're learning how to label the other 2 coordinates. And if you draw it like this with this 3 axes where you're looking down in the thing, it's counterclockwise. And so x, y, z counterclockwise. So this is x, this is y, and that's z. And that's the right-hand rule. If I go in X and I cross Y, then I get Z. So my right hand puts this one is X, this one is Y, and this one is Z. If I did it with my left hand, then it would swap the Y-axis, and it would mess things up. So we have right-handed coordinate systems. Does that mean that nature has to obey that? No, but our character tables are written that way. So if you want to get things correct, use the same handedness as the character tables. So it was whoever decided on those character tables, it was a right-handed system. Sorry, left-handers. This is not a moral statement. Okay, so notice that this cloud is symmetric in all directions. It's the same color going in Z, the same color in X and Y, and so it's going to be top row. And so that's why this one is an A1 orbital, okay? But notice down here, I have the Z-axis coming out, X here, and Y here. And these orbitals are, you can think of them as oscillations of the electron cloud. And so let's just say that red is expanding. And green equals contracting. So what if I shrink that green and I expand the red? Can you see an arrow appear? Like this green, if it shrinks like water, if it's flowing through the molecule like this, then most of the electron cloud is moving up, right? At some nanosecond or picosecond later, it's going to reverse. Otherwise, the electrons are going to flow off the molecule. They're going to get too far away from these positive nuclei, and they're going to come back. And when they flow back, the green will expand. It'll change to red, and it will expand, and the red will change to green because it's contracting. And so these are going to blink. They're going to go green, red, green, red, green, red. And that's flowing of the electron cloud in what direction? Look at the coordinate system. Y. So you look at that and you say, Y. That's changing in Y. Therefore, that's an E motion. So this molecular orbital is E symmetry. We could do exactly the same thing for this version over here. And it's flowing back and forth, left and right. And that's the X direction. And so that's also E. It's that easy. Okay? If I give you a MO, you should be able to look at it and look at the coordinate system and say, where are the green and reds going? Are they sloshing along the x-axis? Are they sloshing along the y-axis, z-axis? Then you go to the character table and you find the way they're sloshing. And you now know their symmetry. And then that allows you to do that transition dipole moment integral, which we're going to do next. Okay. And so if we're given, this is what I'm saying, if I give you an MO picture, you should be able to assign the symmetry using the Mulliken notation. And so you could come down here and you could say those are the same as X and Y, therefore they're E. This one is symmetric in all directions. It's expanding out and contracting in. You can kind of think of it as, what's the equation of a sphere? X squared plus Y squared plus Z squared. And what do you see over here? X squared, Y squared, Z squared. Okay, so this sort of same in all directions. You could also say if I do a C3, the colors don't change, and so I have a positive character there. If I do my 3 reflections, I have no change, and so I have a positive 1 there. And so these positive 1s can kind of help you decipher it. So that's another way to do it. Here's the molecular orbitals for water. You would show these in the lab. And so it'd be great if you went, well, part of the lab is to take all of these molecular orbitals and the symmetries are there, but go ahead and, on your own and compare them to the character table. And you can see, hopefully, that you've got, Y motion here, and so that's B2. This one, we've rotated the molecule 90 degrees, so this is X motion. And so then that's B1. This is up and down on the Z-axis, and so that's A1. This is fully symmetric in all directions, and so that's also top row. So you should be able to go to the character table and see all of these molecular orbitals and say, oh, I see how this works. And we're going to develop this throughout the whole semester. As we get into molecular orbital theory, that's what we're showing here is the molecular orbital diagram for water. Okay. You will be, by the end of the course, able to draw this from scratch, like take the atomic orbitals and put them together and create all the molecular orbitals. So let's look at these. So I've kind of put a flow chart in the notes to try to determine the symmetries. And so if you put yourself at the origin, let's do this one right here. If I'm standing at the origin and I look up and I look down, I look up and I see green and red on either sides. I look down, I see green and red. There really is no change along Z. If I look left and right in terms of Y, I looked left in Y and I see green. I look right and I see red. So there was a change in the Y direction. And I look in X direction, I look forward, I see a split with green and red on either side, and I look back in Z and I see the same thing, so there's no change along X. And so what we're looking at in this flow chart is the positive X and the negative X direction the same? Yes, it might be X squared. No, it's X. And so that's good. Or in this particular orbital that we're looking at, it was yes, it was the same. So we're looking at this one. I look out in the X direction. It looks the same forwards and backwards. And so that would be X squared. In the Y direction, though, we change color. And so I would say that it's Y. In the Z direction, that was the same. And so here's this first question. Is there a single X, Y, or Z symmetry, and there was a Y symmetry. Then choose the X, Y, or Z row of the character table. And so we choose that Y row, and it was B2. So this is just a little flow chart of the thinking when you're looking at those molecular orbital diagrams, or the molecular orbitals. Now let's practice on assigning some of these. So here's a different molecule than water. This is formaldehyde. Here we have the coordinate system. It's actually on the center of mass this time. So let's look at the z-axis. So we have a change in z here with these arrows. First of all, we see arrows, don't we? So this is vibrational motion. Here we see the green and red clouds. This is a molecular orbital. That's a very basic thing, but if I don't say it, you might not pick up on what's being shown. Okay, so then these arrows are both going down, but they're going out opposite of each other, so the Y components cancel. And we have a change in dipole moment along the Z-axis. So at some time later, it'll change direction, and it'll oscillate up and down the Z-axis, and so that's Z symmetry. Now, if we take this molecule through the flow chart, can you, I know it's kind of new to you, but can you tell what the point group would be for this molecule? It's not linear, okay? It does have some rotation, but it doesn't have a lot of rotational axes. Does it have, what is the rotational axis for this molecule? C2, very good. Is it 180 degrees? We'll put those hydrogens on top of each other. So it'll swap the hydrogens with a 180. And then it doesn't have any perpendicular C2s because the top of the molecule can't rotate into the bottom because there's no hydrogens, and the oxygen and carbon are different. So it's just got one axis, it's the C2 axis. Then we get to a question block about, does it have, if it's a C2, n equals 2, does it have n vertical reflection planes? So it should look, we're looking for 2 vertical reflection planes. We have one right here, okay, left and right, and then we have the plane of the board. The top and the bottom of the molecule are the same. So it has 2 reflection planes, a C2 axis, it's C2V. Then we get to the end of that flowchart, it's C2V. So it's just like water. Now think about water, an oxygen and 2 hydrogens. Doesn't this molecule look like water? In your mind, if you look at this and you go, okay, I see water. It has a C2 axis, and the left and right are the same, the front and back are the same, but the top and bottom are different. And that's it. If you can look at this and compare it to water, and you know water C2V, this is C2V. If you've got a molecule that's really complicated, like O-phenanthroline, it's a nice little chelating agent for iron. We use it in UV-Vis determination of iron, like in vitamins and stuff. Really complicated looking molecule. And then there's some electron delocalization in here. Okay, that's how a P chemist draws organic molecules. As a joke. Okay, so you look at this molecule and you compare it to water. Do you see the comparison? It has a C2 axis. The left and right are the same. The front and back are the same. The top and bottom are different. Okay, it looks just like water. And so that's my Jeff Foxworthy joke. If you think O-phenanthroline is just like water, you might be a P chemist. Because chemically they're not anywhere near the same, but symmetrically they are. Okay, C2V, they have the same symmetry elements. All of their molecular orbitals will be A1, A2, B1, or B2. Okay, and so then here we have C2V. So C2V, the Z-axis, that's going to be A1. So this motion is A1. Same here. Do you see the sloshing up and down on this molecule along the Z-axis? So this molecular orbital is going to have Z symmetry and also be A1. Let's look at a different one. Here, the arrows, vibrational motion. Do you see now that they're moving on the y-axis? The up and down parts cancel, but the y part doesn't. And so that's going to be Y symmetry is B2 in a C2V character table. And then the same thing, this is sloshing back and forth along the y-axis. So it is Y symmetry. So that's just some practice on assigning symmetries. Let me just review again. For vibrational motion, this bottom one was A1. So V equals 0, V equals 1 is B2. In order to get a spectroscopic selection rule that's non-zero, okay, we need to use a particular symmetry of light. So what goes in here? And that's what we're going to do next time, is really focus on, now that we know the symmetries of our orbitals, our lower state and our upper state, what goes in the middle so that we have an allowed transition. And if we can't put any light in the middle that gives us a non-zero result, then that transition's forbidden. Even though light, a photon of light might match the energy difference, symmetry won't allow it to be absorbed. Okay, and in big molecules, symmetric molecules like benzene, like half the transitions are not allowed by anything. So even though there's vibrations, they can be excited by collisions. They can't be excited by light because there's no oscillation of the dipole moment with that vibration. And so this is where we're going next. Today we were just focused on assigning symmetries to the wave functions. And even though these don't really look like wave functions, the arrows and the clouds, that's what they are. You'll have a great day.